I will now talk about data structures for representing disjoint sets. Before I start talking about data structures and the problems, I want to motivate why we care about this. And before this motivation, let's actually introduce a few notations or a few definitions that we have seen before in Comp 182, for example. So imagine that we have a universal set. So I have a universal set U. So this is the set of all elements that I'm interested in. And suppose then I have a set of sets here, S1, S2, all the way to Sk. We say that this set of sets and each one of these Si is a subset, it's a subset of U, okay, for every I between 1 and k. So we say that this set here, S1, S2, all the way to Sk, is a partition of U if for every I not equal to j, Si intersection with Sj is empty, and then the union from 1 to k of all the sets Si, this union gives us the set U back. One important thing is that we don't want any of these Si's to be empty. Okay, so Si also is not empty here. Okay, so this condition here, condition 1, is what we use to denote or to say that the sets are disjoint, pairwise disjoint. No two sets have any elements in common. And we are interested in data structures for representing this set of disjoint sets, and gives us the following operations. It allows the following operations. We want to create a new set with one element. We want to compute the union of two sets. And we want to find the set to which a given element belongs. Okay? So before we talk about these operations specifically, I want to give examples of where we run into these kind of scenarios, that we have a set of sets that are disjoint, and we need to maintain a data structure that captures these sets, and we need these operations. So before that, when I have a set Si, for example, let's say Si is A, B, C, D, okay? We usually are interested in having a representative of that set. So for example, I can write like this: A is the set that contains A, B, C, D. Okay, so here I chose the element A to be the representative of that set. There is absolutely no reason to choose A. I could have chosen B or C or D, but I choose one element and specify it as a representative of that set. Okay, so when I write something like this, X, what I mean here is the set whose representative is element X. Okay, and if I now talk about these three operations that I defined, creating a new set with one element. So for the first one here, we will define make set X. This creates the set. Okay, so it's a set that has one element X, and we can write it as X in square brackets because X is the only element and it is the representative of that set. If I want to take the union, we define union of X and Y. It basically computes the union computes the union of the two sets to which X and Y belong. Okay, so we have two elements, X and Y. We look for the sets to which these X and Y belong, and we take the union. Of course, if X and Y are from the same set, then the union is the set itself. If X and Y are from two different sets, the union is now the set that has all the elements from both of them. And the third operation here is find set of X. And here basically we want to find or return Y such that X is in that set whose representative is Y. Okay, so find set of X is return the representative of the set to which X belongs. Now, where do we encounter these disjoint sets and we need these operations? So I will show three examples here. Example one is the equivalence classes of an equivalence relation So an equivalence relation, we talked about that in compound 82. An equivalence relation is a relation that is reflexive, symmetric, and transitive. So if we have equivalence relation R on set A, we know that this relation defines a set of equivalence classes or partitions A. R partitions A into a set of equivalence classes. So if I want to compute the set of equivalent classes, imagine that R is finite. Okay, let's imagine that R is finite, for example. So it's a finite set of pairs of elements from A, and I want to compute the equivalence classes here. So if I want to compute equivalence classes of the relation R that's defined on set A. How do I compute this? So I can first, for example, for each A in A, I can make each element in A an equivalence class by itself. So I can now say make set A. So now we have defined every element in A as an equivalence class by itself. Now we know that an equivalence class is a maximal set of elements that are equivalent to each other under R. So now I can go through all the elements of R. So for each pair in R, I can now ask if A and B belong to two different sets. So if find set A is not equal to find set B. So A and B, since AB is in R by this line here, if AB is in R, it means that they are equivalent and they should be in the same equivalent class. So now I do find set of A, find set of B. If they are not in the same set, I need now to merge them. I need to union A and B. Okay? So if you look at this algorithm here for computing the equivalence classes, I needed the make set. I needed the make set operation here. I needed the find set here in both of these places, and I needed the union. And notice that equivalence classes are disjoint sets. So at no point am I gonna be taking the union of two sets that are not disjoint. Okay, so when we compute equivalence classes of an equivalence relation, we need to take care, or we need to handle a set of sets that are pairwise disjoint. Okay, so this is one example. So another example from the area of graph theory. Let's talk about example 2. Example 2, we want to talk about the connected components of a directed graph G equal V in E. Okay, so remember that a connected component is a maximal set of nodes such that every two nodes in that set are reachable from each other through a path. So if we want to compute the connected components, so if I want to compute CCs, connected components of G, similar to how we did it with the equivalence relations, first thing is that every node, we declare every node to be a connected component by itself. So we say now for each V in V, we make set V. Okay, so what we did here is that every node by itself is a connected component. This is how we are initializing the algorithm. Now we need to go through these nodes, and every two nodes that are connected by an edge, now we need to start merging their connected components, right? So now we go through for each edge UV in E, we now need to find set of U, and we need to find set of V. And if they belong to different sets, okay, so if they belong to different sets, we need now to take the union of that. Okay, this is really an algorithm for computing the connected components of an undirected graph. Similar to before, we needed these three operations. I needed to make these sets. For every node is going to be a set by itself. I needed to find the set to which a node belongs. And then I needed the union so that I start merging smaller connected components into larger ones. Okay. The third example I want to show is also from the area of graph theory, example 3. Computing the minimum spanning tree, minimum spanning tree or MST of a weighted undirected graph G that's given by V, E, and W. So W is the weight of the edges. V and E are the nodes and edges of this graph. Minimum spanning tree, I remind you, it's a tree, so it's a graph that's connected and acyclic, and the graph spans the tree spans the entire graph, which means every node has to be part of the tree that we return, and it is minimum, as in the sum of the weights of the edges of the tree has to be smallest among all possible spanning trees. Okay. So one famous algorithm for this problem is Kruskal's algorithm. Okay, Kruskal's algorithm that basically takes G, this undirected graph, weighted undirected graph, and computes the minimum spanning tree. How does Kruskal's algorithm work? The first thing is that it says, let's sort the edges. Sort the edges in non-decreasing order. Okay, and imagine that these edges are E1, E2, all the way to EM. So we sort the edges in non-decreasing order. And after this, we do the following. So for example, I can initialize this I to 1 here, and I have the set of nodes. Actually, we will make the set of nodes individual by themselves. So for each V in V, we are gonna do make set V. So we are gonna create, basically every node is a tree by itself. Okay. So here what we are saying is that every node is an minimum spanning tree of basically the graph with that node. Okay, so what we did here is, let me actually number these ones here. 1, 2, 3, and this is A here. So in line 3 and 3A, What we are doing here is that we are putting every node in a set by itself. Now what I will do is we're going to go through the edges in that non-decreasing order, and we are going to start merging sets based on the edges here. Okay, so I will now go. So if suppose we declare actually here on line 2 as well, I declare the set of edges to be empty. So this line here, I'm going to put it in red. E sub t is initialized to the empty set. This is the set of edges of the minimum spanning tree. So now what we are going to do is the following. We are going to say while the size of E sub t is smaller than n, smaller than the size of v. Why am I doing this? Because a minimum spanning tree of a graph that has the set v of nodes, it has to have, if the set v it has n nodes, the number of edges in a minimum spanning tree is n minus 1. Okay, so while the size of the set of edges is not n minus 1, I now need to add edges. How do I add edges using these operations? Now I can, while E sub t is not equal to n minus 1, or it's not equal to n, we do the following now. We are now looking at an edge I here. So let's have EI equal UI VI. So edge EI is the ith edge in this non-decreasing order. And now let's ask if find set UI is not equal to find set VI. Now we can take the union of UI and VI. We know that they need to be, so if UI and VI were in different sets, it means that adding the edge between them to the minimum spanning tree is not going to create a cycle. So we take the union of these two and we can add that edge to, we can do E sub t union this EI. This is really Kruskal's algorithm for finding the minimum spanning tree. And if you look at it again here, what we have is that we first created a set for every node. So if we have n nodes, we created n sets. One important property is that sets, if you merge two sets, it means that there is an edge that connects a node in one set with a node in another set, which means if you add that edge to the minimum spanning tree, you are not going to be creating a cycle in the minimum spanning tree. And this is what the algorithm is doing. So while we haven't added enough edges here, which is the while loop, let's actually take the next edge in the order. We find whether UI and VI belong to two different sets. If they belong to the same set, we cannot add the edge that connects them because that will create a cycle. If they do not belong to the same set, then we can take the union so that we now merge them and say now they are in the same set, and we add that edge to the minimum spanning tree. This is Kruskal's algorithm. And again, if you look at it, what you see is that we are making use of make set, find set, and the union operation as well. Okay, so these are three interesting examples of where we need to maintain a data structure that stores this set of disjoint sets. And we need these three operations on them: make set, union of two sets, and we find the set to which an element belongs. So the question, of course, since we are talking about data structures, is what is a good data structure that allows us to do these operations efficiently? Okay, and this is what we are going to be talking about.